Welcome to AI Paper Slop, where we basically tear through our fire hose so you don't have to.
There is just so much slop out there right now.
There really is. But today, we're doing a deep dive into something actually incredible. It's called FLX, a multi-stream world action model with compute flexibility. This is by Yan and colleagues from UW and the Allen Institute for AI.
And honestly, it's a phenomenal piece of engineering.
Totally. So let's just get straight to the core insight for you all listening, because if you're building world action models or WAMs, you are almost certainly predicting future RGB pixel latents to learn your representations.
Right. That's the standard recipe.
Yeah, exactly. But what FLXX does is discover this massive, basically a free lunch. They add 3D point maps and DINO v3 object semantics to the prediction task.
Which sounds incredibly expensive.
It does. But here is the kicker for the ML practitioners out there. They do it without adding new depth sensors to the robot, without pre-training any new visual priors, and crucially, without adding a single millisecond of inference latency at deployment if you don't want it to. And they are seeing 2 to 6x performance jumps on real-world precise tasks.
Which, that fundamentally shifts how we should think about generalist robot policies.
Yeah.
Because historically, we've dealt with this massive tension between vision language action models, so VLAs, and world action models.
Better classic trade-off.
Exactly. Your standard VLAs, they scale beautifully on internet data, right? But because they don't predict the future, their internal representations remain somewhat shallow.
Right. They kind of struggle with complex, multi-step physical reasoning.
Precisely. Now, WAMs fix that by forcing the model to hallucinate the future state of the world. That prediction acts as a really powerful regularizer for the internal representation.
But they're usually bottlenecked because they're only predicting flat 2D RGB latents. So the model knows what the future, looks like, but not necessarily the physical geometry of it. So FLAX essentially asks, well, what if we force the model to explicitly understand 3D geometry and semantic objects, but we trick the architecture into absorbing those heavy compute costs during training rather than at deployment?
Yeah. And that's the core thesis. But to understand how they actually pull that off without, bolting expensive LiDAR or depth sensors onto the robot, we have to look at their back-end pipeline.
Right, the data prep.
Right. So they extract these 3D point maps using an off-the-shelf depth anything 3 estimator. And this is running purely on standard 2D RGB camera input.
Okay, I follow that. Depth anything 3 is incredibly robust now.
It is.
But here is the part of the paper where I really have to push back, because mathematically it sounds impossible.
I know exactly what you're going to say.
Right, because they take those synthesized 3D point gaps and they feed them into a frozen variational autoencoder, a VAE. And they take this from a pre-trained video generation model called WAM 2.25b. Now, this VAE was trained exclusively on 2D RGB pixels from flat internet videos.
Zero 3D data.
Zero. It has never seen a point cloud, yet the paper shows this frozen unit encoding and reconstructing 3D point maps almost losslessly.
It's wild.
It is. How is that latent space not just treating the point map as a weird, corrupted 2D image? If I use a JPEG compressor on a CAD model, it's going to ruin it. Does it actually preserve the structural geometry?
So it's an incredibly counterintuitive finding, right? But if you break down what a video generation model is actually forced to learn during its pre-training, the mechanics become clear.
Okay, walk me through it.
Think about what it takes to predict temporal pixel shifts accurately over time. To generate a coherent video of a car driving behind a building, the model can't just memorize 2D pixel patterns.
Right, because the car has to disappear and reappear correctly.
Exactly. It is mathematically forced to invent an internal representation of occlusion, perspective shifts, depth ordering, all of that.
Oh, wow. So it's essentially fossilized geometry, like leftover spatial rules the model had to invent just to make 2D videos look realistic?
Precisely. The VAE's latent space has already carved out this high-dimensional manifold that natively accommodates structural geometry. So when you feed it a point map, you aren't fighting the unit.
You're just slotting into it.
Yeah, you're actually projecting into the implicit 3D structure it was already forced to learn at internet scale.
That is just wild to me. It's exploiting the physics engine that naturally emerges inside video models. Okay, so we have these distinct streams now.
Right.
We have our standard RGB latents, we have our surprisingly accurate 3D point map latents, and we have our DINO v3 semantic tokens.
Yep.
And for anyone listening who is unfamiliar, DINO v3 provides these deep object-centric features. So it's not just geometry, but an understanding of what the object actually is.
A mug versus a bowl, yeah.
Exactly. But having all these rich streams creates a massive architectural challenge. I mean, how do you fuse them efficiently without your attention mechanism just grinding to an absolute halt?
Well, you can't just mash them together. If you naively concatenate all of those streams, your sequence length explodes and your compute costs go through the roof.
Standard transformer problems.
Right. So to solve this, FLAXCO uses a mixture of transformers architecture. They embed all the tokens into a single shared space using a 5 billion parameter visual transformer backbone.
Yeah.
And again, this is initialized directly from WAN 2.2.
But the actions aren't processed in that same visual backbone, right?
Correct. They isolate the action tokens into a separate 1 billion parameter action expert transformer.
Okay, makes sense.
So the visual backbone handles the heavy lifting of spatial temporal fusion, basically figuring out how the scene is changing. And the action expert is specifically tailored to cross-attend to those visual streams and output the actual motor commands.
Got it.
And they actually only allow cross-stream attention in the middle 16 blocks of the 30-block backbone. So the early encoding and late decoding stages remain entirely stream-specific.
That makes total sense for routing, but the DINO stream processing is what caught my eye from a pure engineering standpoint.
Oh, the folding.
Yeah, because to keep the sequence length manageable, they implemented a pixel unshuffle style folding. So they take a 2x2 patch neighborhood of DINO features, and they fold it into a single token.
Right, which cuts the sequence length by 4x.
Which is fantastic for your attention compute.
Mm-hmm.
But the trade-off is it balloons the dimensionality of those tokens from a standard 768 all the way up to 3072.
Which instantly breaks standard diffusion training.
Exactly. And this is a huge point for the ML engineers dealing with diffusion right now. Because of this massive 3072 dimensionality, the researchers had to actually abandon standard flow matching velocity prediction for that specific DINO stream.
Yeah, they couldn't use it.
Right. They swapped it out for something called X prediction, where you predict the clean features directly. So I understand that high dimensions are computationally heavy, but why does the actual math of velocity prediction break down here? Is it a variance issue, or does the vector just get lost in that much space?
It is entirely a variance issue, and it really reveals a fundamental limit of standard flow matching.
How so?
Well, in a typical flow matching setup, you are regressing the velocity vector. That's the path that points from pure noise directly to the clean data manifold.
Right.
In lower dimensions, that vector is relatively stable. But in extremely high dimensional spaces like 3072, the variance of that target velocity vector just explodes.
The optimization landscape gets chaotic.
Incredibly steep and noisy.
Because any tiny error in your velocity prediction gets compounded massively as you step through the diffusion process.
Exactly. When you integrate that noisy velocity vector over multiple time steps to generate an output, those small numerical errors compound rapidly, and the generation just collapses.
Right.
So by scanning to X prediction, which is directly predicting the ground truth clean data itself rather than the velocity, you bound the error. You shift the objective from trying to learn a highly sensitive gradient field to directly anchoring on the stable data manifold.
Oh, wow.
Yeah, and that stabilizes the joint generation process across these vastly different modalities.
Okay, so they use standard velocity flow matching for the lower dimensional RGB and point map latents, but they use X prediction to keep those massive DINO tokens from derailing the whole training run.
That's the trick.
That is an incredibly elegant compromise. But stabilizing the training is only half the battle, right? I mean, if you train a policy on RGB, depth, and semantics, that policy naturally expects to see all those streams at inference time.
Yeah, and that is the classic deployment trap. Generating a 3D point map, extracting DINO features, and running a massive UNet at 30 Hertz on a physical edge device.
It's a latency nightmare.
Absolute nightmare.
So how do they avoid needing all these heavy inputs when the robot is actually out in the real world?
So they utilize a combination of visual stream dropout and a technique they call cross-modality forcing.
Okay.
During training, they define two independent binary masks per sample. There's an input presence mask and an output attention mask. For the input side, every single visual stream, so RGB, 3D, and DINO, is independently dropped with a 50% probability.
Okay, so just standard dropout. That forces the model not to over-rely on any single sensor.
Right. But the genius part is on the output side. Crucially, every future stream is always denoised at the output, and incurs a flow matching loss, regardless of what was observed at the input.
Wait, really?
Yeah, that's the cross-modality forcing. The model must synthesize a missing modality's future from whatever remaining streams it has.
Okay, so if the 3D point map input is randomly dropped by the mask during a training step, the model is still forced to predict the future 3D point maps using only the RGB and DINO inputs it has left.
Exactly.
That is so cool. I was thinking of it like training a chef blindfolded.
Oh, that's a good way to put it.
Right, like you force them to learn to cook relying entirely on smell and touch.
Yeah.
By doing that, you are forcing them to internalize the underlying chemistry and physical properties of the food rather than just reacting to how it looks.
Yeah.
So when you finally take the blindfold off, they are a fundamentally better chef because their internal model of the cooking process is infinitely deeper.
That is spot on. And practically, this cross-modality forcing creates a truly universal checkpoint. Because the model is constantly forced to hallucinate missing 3D and semantic data during training, it internalizes those geometric and object-centric representations deeply within the shared UNet trunk.
Right.
So even when you drop the 3D point map and DINO inputs entirely at inference time to save compute, your action tokens are still benefiting from that forced geometric understanding the trunk gained during training.
The core representation itself has just been irrevocably upgraded.
Exactly.
So how does this actually translate to real-world performance? Because, the ultimate test of this one-checkpoint-fits-all approach is on actual hardware. They evaluated FLSX on a bimanual YAM robot, and the tasks they chose are brutal. We aren't talking about pushing blocks across a table.
No, these are highly dexterous millimeter precision challenges.
Like, let's highlight the self-repair gripper task. The robot literally has to pick up an electric screwdriver, grab a replacement 3D printed gripper finger, align it with the mount hole, and screw it in.
It's crazy.
We're talking about plus or minus 0.25 millimeter clearance for the insertion.
And a task like that requires an incredibly robust understanding of spatial geometry and contact forces. A purely 2D representation almost always fails there because it just lacks the depth estimation.
Right. And they also tested it on a soft bag zipping task. So the robot has to open a deformable pencil case, put a pen inside, and zip it shut.
Which is so hard.
Right. Deformable objects are notoriously difficult because their state space changes chaotically with every single physical interaction. How did FLEX handle it compared to the state of the art?
It absolutely dominated. Across the board, FlexX beat baselines like Pi 0.5, fast WAM, and even a 3D native policy called ManaFlow by 2 to 6 times in task success rate.
That's huge. But
Yeah.
here is the Pareto frontier trade-off that is so valuable to me. Because of that masking strategy we discussed, you can choose your deployment mode using the exact same checkpoint. You can run in action-only mode. This skips predicting the visual futures entirely. It just takes the input and outputs actions, and it runs blazingly fast at 60 milliseconds per call.
Which beats P 0.5 on both speed and task success, by the way.
Exactly. Or you can toggle a flag to run in full joint prediction mode. This forces the model to predict the future RGB, 3D, and DINO latents alongside the actions. It adds latency, obviously, but it boosts average task success by an additional 13%.
And we should also note that the representations are so rich that it heavily dominates on data scaling, too.
Oh, right, the RoboTwin benchmark?
Yeah. On RoboTwin, they restricted the data budget to just 50 and 100 demonstrations per task. FLXX outperformed the baselines by almost 2 to 4 times at those extremely low data regimes.
That is wild. I have to play devil's advocate here, though. If the action-only mode is already running at 60 milliseconds and beating the 3D native baselines on success rates, why would an engineer ever deploy joint prediction at inference?
It's a fair question.
Right, like, is a 13% boost in success really worth the latency hit? Because in real-world robotics, lag causes physical collisions. The physical world does not pause while your 6 billion parameter model is busy hallucinating future point maps.
No, it doesn't. And that is the exact tension every roboticist faces. The answer depends entirely on the operational environment.
Okay.
Think of it like System 1 and System 2 thinking in human cognition.
Okay, I like that.
Action-only mode is your autonomic nervous system. It's highly reactive, time-sensitive control. You use it for, like, catching a falling ball.
Right. Fast reflexes.
But joint prediction is deliberate. System 2 thinking. You toggle joint prediction on when the robot encounters out-of-distribution states, or when it needs to perform highly complex spatial reasoning where getting the exact geometry right is far more important than raw speed.
So for the self-repair gripper task, where you have a 0.25 millimeter clearance, that 13% success boost is literally the difference between successfully repairing the robot and snapping an expensive tool in half.
Exactly. And the beauty of FLAX is that you aren't forced to maintain two separate training pipelines for these regimes. You just change a runtime flag based on the task context.
That's super clean. Okay, but speaking of latency, getting a 6 billion parameter model to run at 60 milliseconds per call is not trivial.
Not at all.
You can't just rely on standard PyTorch eagerly executing the code and hope for the best.
No, the researchers had to heavily engineer the inference stack to optimize for edge compute, because generating actions via flow matching isn't a single forward pass. You have to solve an ordinary differential equation, an OD, to trace the path from pure noise to a clear action step by step.
Right, and they use Euler integration for this, and they empirically found that the optimal number of steps is k=4.
Yep.
If they drop it to k=1 to try and save time, task success literally collapses below 60%. So they are hard-locked into running 4 forward passes of a 6 billion parameter model per action chunk.
Which is heavy.
Very heavy. So to make that viable, they implemented a pre-filled decode split.
Which is a classic optimization we see in large language models for KV caching. But applying it to the denoising steps of a diffusion model is incredibly clever.
Yeah, I thought that was super smart. They realized that out of the tokens being processed, 387 of them are anchor tokens. So things like the language instruction and the robot's proprioception.
Stuff that doesn't change.
Exactly. Those tokens don't change during the 4 denoising steps. So they pre-fill those once, cache the keys and values, and only decode the 806 noisy latent tokens during the forward passes.
Nice.
That alone cuts the per-step computation cost by 27%. But the optimizations actually diverge drastically depending on which mode you are running.
And this is where profiling your specific bottleneck becomes crucial.
Yeah, for the ML engineers listening who are trying to deploy diffusion models on edge compute today, this is essentially a masterclass.
Totally.
So for the action-only optimization, the researchers found the dominant lever wasn't making the matrix multiplication faster. It was actually loop scope compilation.
Oh, interesting.
By capturing the entire denoise loop and the key value prefill into a single CUDA graph, they dropped the per-step cost 3.5x, from 14.2 milliseconds down to a tiny 4.1 milliseconds. Wow. But for the joint path optimization, where you are generating all those visual features, the bottleneck shifted entirely. There, they had to export the 30-block denoise core to Tensor engines to basically attack the per-step FLOP cost. So why such a drastic difference in strategy?
It comes down to understanding CPU to GPU launch overheads versus raw math bounds.
Okay, unpack that for us.
In joint generation, your model is actively imagining over 1,000 tokens of visual futures, right?
Right.
In that regime, your GPU is working incredibly hard doing massive matrix multiplications. You are FLOP bound. Kernel Fusion and Tensorite are your best tools there because you just need to make the math faster.
But in action-only mode, you aren't predicting visuals. You only have about 32 action tokens.
Exactly. The math is incredibly fast. In fact, it's so fast that your GPU finishes the calculation and is left starving, just waiting for the CPU host to tell it what the next step of the loop is.
Oh, so it's a communication bottleneck.
Exactly. That CPU to GPU communication latency is the host glue, and it is absolutely the silent killer for small sequences. A CUA graph solves this by capturing the entire denoising loop into a single compiled execution plan.
Got it.
You launch it once, and the GPU executes all 4 steps without ever talking to the CPU again. That's why they saw a 3.5x speedup. The optimizations for a reactive policy are just fundamentally different from the optimizations for an imaginative policy.
Action only is launch bound. Joint generation is FLOP bound. That is a phenomenal takeaway.
It really is.
All right, let's wrap this up. The sheer elegance of the FLAX approach is honestly staggering. By creatively exploiting the U-net of an existing video model, they realized the network had already learned the 3D structure of the world just from watching 2D internet videos.
Yeah.
They extract that geometric and semantic grounding essentially for free.
It completely reframes how we view the utility of pre-trained foundation models.
Right.
Like, they're so much more than what they were explicitly trained for.
And by using clever masking and cross-modality forcing during training, they yield this incredibly flexible policy. One single checkpoint that scales from 60 millisecond autonomic reflexes all the way up to deep multimodal spatial reasoning, beating state-of-the-art baselines on sub-millimeter insertion tasks.
It really proves that the bottleneck in robotics isn't always hardware or sensor fidelity.
Right.
Sometimes it's just about forcing the architecture to internalize the right representations.
Which leaves us with a final, slightly provocative thought for you to mull over. If a pure video generation VAE natively encodes 3D geometry accurately enough for a robot to perform a plus or minus 0.25 millimeter screw insertion task, what other physical properties are already hiding in the latent spaces of today's video models?
Oh, that's a good question.
Right, like, is there a manifold for mass, for surface friction, for material tension? Are the core physics of our world already mathematically fossilized in these units, just waiting for the right projection head to extract them?
Once you start looking at these latent spaces as physics engines rather than, just image compressors, the possibilities are just endless.
They really are. Well, that's it for this deep dive on AI paper slop. Keep building, and we'll catch you on the next one.